The CARNOT cycle. Having defined the reversible process and considered some factors that make processes irreversible, let us again pose the question raised in the section 3. If the efficiency of all heat engine is less than 100, what is the most efficient cycle we can have? If the efficiency of all heat engine is less than 100%, what is the most efficient cycle? We can have. Let us answer this question for a heat engine that receives heat from a high temperature reservoir and rejects heat to the low temperature reservoir. Since we are dealing with the reservoirs, we recognize that both the high temperature and low temperature of the reservoir are constant and remain constant regardless of the amount of heat transferred. As a definition for a reservoir, let us assume that this heat engine, so we have receive heat from a high temperature and second and reject heat to a low temperature reservoir. The reservoirs are at same temperature. Or at constant temperature. Reservoirs. Since we are dealing with the reservoirs are in constant temperature regardless of the amount of heat transfer. Let us assume that this heat engine which operates between the given high temperature and low temperature reservoir as shown. High temperature and low temperature reservoir does so in a cycle in which every process is irreversible. If every process is irreversible, the cycle is also reversible, and if the cycle is reversed, the heat engine becomes a refrigerator. In the next section, we will know that this is most efficient cycle that can be operated between two constant temperatures. It is called the CARNOT and is named after French engineer Nicolas Leonard Sadi Carnot. The most efficient cycle under the curve between this temperature is Carnot cycle. And is named after a French engineer Nicolas Leonard Sadi Carnot. Who expressed the foundation of the second law of thermodynamics in 19th century. We now turn our attention to the cycle Carnot cycle. The Carnot cycle was shown in the next picture. Carnot cycle. This figure shows a power plant that is similar in many respects to a simple steam power plant, and we assume operate on the Carnot cycle. Consider the working fluid to be a pure substance. Working fluid is a pure substance such as steam, for example. Heat is transferred from the high temperature reservoir to the water stream in the boiler as shown in this picture. QH transferred from high temperature reservoir to the boiler, and for this process to be a reversible heat transfer, the temperature of water must be the only infinitesimally lower than the temperature of the irreversible condition. The temperature of steam must be close to the high temperature reservoir. The reversible case, the temperature of water steam must be only infinitesimally lower than the temperature of the reservoir. This result also implies, since the temperature of reservoir remains constant, that the temperature of water must remain constant. So the temperature for constant. So the temperature for steam also be constant for having a reversible process. Therefore, the first process in the Carnot cycle is a reversible isothermal process in which heat is transferred from the high temperature reservoir to the working flow. Isothermal reversible. A change of phase from liquid to vapor at constant pressure is, of course, an isothermal process for a pure substance. Also before change of phase. The next process occurs in the turbine without heat transfer and is therefore adiabatic. Let me show the turbines. Next process is occur in the turbine adiabatically. Since all processes in the Carnot cycle are reversible, this must be a reversible adiabatic process. Reversible. For the next working in the turbine. This must be a reversible process during which the temperature of working fluid decreases from the temperature of high temperature reservoir to the temperature of the low temperature reservoir. In this process, the temperature decreases from high temperature reservoir temperature to the temperature of the low temperature reservoir, to the temperature of low temperature reservoir. In the next process, it is rejected from the working fluid to the low temperature reservoir. Let me provide the picture here. Consider these filled arrows. The temperature in the turbine reduced to the temperature for the condensate TH, for example. This is we have TL during the turbine, and the non-filled arrows also show same direction. In the next process, heat is rejected. 3. From the working fluid to the low temperature reservoir. Reservoir. This must be a reversible isothermal process in which the temperature of working fluid is infinitesimally higher than that of the temperature of reservoir. The most reversible isothermal process from, for example, TL plus DT to TL at the condenser to the reservoir. During this isothermal process, some of the steam is condensed. Some of the steam condenser. The final process which completes the cycle is the final process which completes the cycle is a reversible adiabatic process in which temperature reversible adiabatic process which increase temperature fluid temperature to the high temperature reservoir high temperature in this case we have a pump, for example. If this were to be done with water as the working fluid, a mixture of liquid and vapor would have to be taken from the condenser and compressor. This would be very inconvenient in practice, and therefore in all power plants the working fluid is completely condensed in the condenser, the pump handle only the liquid phase. Since the Carnot heat engine cycle is reversible, every process could be reversed, in which case it would become a refrigerator. Since the all process in Carnot cycle the heat engine, the cycle is a process can be reversed or could be reversed. In which case it would become a refrigerator. Refrigerator is shown by the dotted arrows and text in parentheses. The temperature of the working fluid in the evaporator. We just talk about the refrigerator with the dotted arrows, and also the not below ground. Temperature of working fluid in the evaporator would be infinitesimally lower than the temperature of low temperature reservoir, and in the condenser it would be infinitesimally higher than that of high temperature reservoir. It should be emphasized that the CARNOT cycle can in principle be executed in many different ways. Many different working substances can be used, such as gas or thermoelectric devices, such as described in the previous chapter. There are also various possible arrangements of machinery. For example, a Carnot cycle can be devised that takes place entirely within a cylinder using a gas as a working substance. The important picture that describes the various stages in the Carnot cycle is as this picture, as shown in the picture. At first, we have irreversible isothermal expansion, also here, and isothermal process, adiabatic expansion. We had adiabatic expansion in this section, which is a turbine work in the cyclic power plant, and at the next we remove the masses to this point. After that we can add the masses and start a isothermal compression, reversible, to goes to the initial case. In this case we have also a Carnot cycle. The important point to be made here that the Carnot cycle, regardless of what the working substance may be, always have the same four-stage process. So regardless of what the working substance may be, always has the same four basic. For Carnot we have always four basic process. For Carnot cycle, the first one, irreversible isothermal, process in which heat is transferred to or from the high temperature reservoir. The second is a reversible adiabatic process as shown here. In which the temperature of the working fluid decreases from the high temperature to the low temperature and third one, a reversible isothermal. In which heat is transferred to or from the low temperature to or from the low temperature reservoir. And a reversible adiabatic in which the temperature of the working fluid increase from the to the high temperature reservoir temperature. The CARNOT cycle stages. The next section is about two propositions regarding the efficiency of a CARNOT cycle.